All right, so we are discussing the second part of the fundamental forces notes. Currently, I am talking about the common names of electromagnetism and going into why each of them is in fact electromagnetism. So, air friction. Why? What I want you to see is that, okay, Spainhour is made out of atoms. On the outside of all atoms are, what's that? Electrons, correct. Air is made out of atoms. On the outside of all atoms are electrons. What do electrons do to electrons? They repel. That's why air friction happens. Basically, if you want to put next to it, negative-negative interaction here. Meaning, if I walk this way in the room, okay, which way is friction pushing me? If I walk this way in the room, which way is friction pushing me? The other, and vice versa. If I fall down because of skydiving, which way is air pushing me? Up. Correct. Or if I jump up into the air, it's pushing down. It just goes the opposite because it's negatives pushing on negatives. Why does water, technically, it's not called friction in that case, it has another name, but it is the exact same thing. Why does water push more? What's that?
More atoms.
Correct. There's more atoms, there's more negatives, and therefore it puts more force back on you, so it's harder to walk through water than it is to walk through air. There's simply more atoms. Technically speaking, if we had enough oomph, we could walk through that wall over there, right? But it's hard to do because there's even more atoms in that spot, pushing back even harder. Now, surface friction is probably the first tricky one. The pictures that I'm going to use today, I did the other day, I know I'm still going to do them again. They are, how did I put this earlier in the first hour? If a chemistry teacher saw me doing the basics of these pictures, I think they would be disappointed at the level of basic that I'm doing. But honestly, it's to my credit here, I think that they're understanding with these basic pictures what's going on when you touch something or grab something is an excellent way of understanding these things. So imagine one object with positives and the next one with positives and also negatives in both of them, and positives and negatives hold on to each other. Now, the example I gave you the other day was putting your hand across the table, but you use surface friction all over the place. For example, the fact that you're currently holding on to the pen at all is surface friction. The positives in your fingers are holding on to the negatives in the pen, and the positives in the pen are holding on to the negatives in your finger. They're grabbing hold of each other, which is why you're able to hold it right here. Don't believe me? Well, when does it fall? When the positives and negatives get too far away from each other, and they can't apply that kind of force anymore. Surface friction is technically the reason why the pen or pencil that you're using right now leaves a mark on the page. The lead has positives, it holds on to negatives in the paper, and vice versa, and it holds on that specific spot very well. And so, to the point that, okay, then what's an eraser? An eraser holds on even better. So when you take the eraser and rub it next to it, you use the friction, the positives in the eraser, to grab the negatives in the paper and the lead, and take that and rip that off of the other material so that it goes away. Surface friction is used all over the place. Basically, two materials make contact, they're in surface friction. You experienced this, I said the other day, with the tape example, but in a more real sense, if you've ever done laundry when it's colder outside, you can experience this exact same thing. Because if you do laundry when it's cold outside and you don't use a dryer sheet, which we can talk to if we get to electricity, hopefully we get to electricity, what you'll find is that there's clothes that hold on to each other. Why? Because they got close to each other, positive held on to the negatives, positive held on to the negatives, and one side won that tug of war. All right, now, negative over here. The other day, I think I told you this was force normal, and it is and it isn't. There is a time to use force normal, and there's a time to use the other thing that we have on this. We'll get to here in just a second. Force normal is going to be very specific, though. We're going to say it's force normal when you're dealing with a solid, immovable object. Like right now, I am being pulled down to the earth by the entire mass of Earth. We call that force of gravity. But obviously, I'm not going that way. What's keeping me from going that way? The floor. Specifically, you zoomed in, the electrons in the floor pushing on the electrons in my feet. We call that force normal when it's a solid, immovable object. So we would say that's the floor. Or if I ran into the wall, that would be force normal. Or if I could jump and run into the ceiling, that would be force normal. But I think we were, and this is where we ended the other day, wasn't it? So I don't know if I got to this example or not. What if my pen is just sitting here? Well, I'm going to go ahead and say that Spanauer's hand is not a solid, immovable object. And technically speaking, you apply enough force, nothing's immovable. I get it, but okay. But it's electrons on electrons. Yeah, but there's a little bit when we talk about these forces of artistic expression, meaning like what you could call them something different than somebody else and still understand it completely fine, as long as you truly understand what it really is. There's negatives in my hand, there's negatives in this pen, and they repel each other. Does that make sense? We'll talk more about this on the next set of slides. Oh, let me go back and remind you real quick. So interactions, air is negative, negative. Surface friction is positive, negative, attracting towards each other. Normal, once again, is negative, negative, repelling each other. So just a heads up, you can have multiple force normals on an object. For example, if you had a dog, you want to play the video or what? You're killing these ones. It's laying on the ground. Currently, there's a force normal pushing up because of the ground. Right? But let's say the dog has a dream, and it's chasing something, and it wants to catch the thing in dreams. So it goes, and goes, and it goes, and eventually it wakes up. So it keeps going. It runs into the wall. Okay? While it's in contact with both the ground and the wall, we would say there's two different force normals in that case, because the electrons of the ground are pushing up and the electrons on the wall are pushing back. But that's while it's in contact. Obviously, when it's done getting hit by the wall, there would no longer be force normal of the wall. All right, next one, tension. Tension is typically seen by ropes, strings, or cables. Okay? Now here's what I want you to do. I have a rope, string, or cable right here, okay? And I've got a mass hanging from it. Which way is the string pulling this? Up. Which way is the string pulling my hand? Down. Or it's pulling inwards. The reason why this is if you zoomed in crazy far, what you're going to see is these lineup of atoms. Let's do another crappy picture here that chemistry people will get irritated at me about. Okay? Let's say, like, again, terrible example. Nucleus, there's negatives on the outside. Nucleus, there's negatives on the outside. Nucleus, there's negatives on the outside. Again, terribly simplified. But what does this positive do to those negatives and this positive do to those negatives? Attract. Because of that, they kind of form, if you like this analogy, you guys ever played Red Rover when you were younger? It's a super violent game where you like line up and somebody tries to run through you. Okay? Basically, they Red Rover that beast. Okay? One pulls on one side and pulls the next, pulls the next, pulls the next, all down the line. We just call that tension. Now, while we call that tension, what did you call it when you were in chemistry, the attraction between the nuclei and the electrons? Come on. Again, this is one of those things that if you were awake during chemistry, you heard this at least 100+ times. What did you call it in chemistry when positives and negatives attracted? Really, nobody? They're called bonds, guys. Like ionic bonds and covalent bonds. Instead of calling it bond, I don't give a crap who your teacher was. Listen, you can put responsibility of understanding on your teacher, but when it comes to some basic things, again, if you were alive and at least around a chemistry room, you don't get to blame the teacher. And quite frankly, if you blame the teacher on that particular fact, that tells me everything I need to know about your education. It has nothing to do with the teacher and everything to do. All right, moving on. Let's move on past that. Okay, so positives and negatives attracting one another causes tension. So going back to this guy up over here. Okay, so positives and negatives holding on. On the opposite side of things, compression is the opposite. Now, here just a second, let me show you, and then you can copy this down. It doesn't take much to copy this down. So I said tension was in ropes or cables. Certainly doesn't have to be. I could take this marker and attempt to pull it apart. Why doesn't it go apart? Tension. Okay? If you are the attraction of two particular individuals, romantic styles, and one's pulling on one arm and one's pulling on the other and they're pulling you apart, you are in tension. It is your bonds that are holding you inward. Compression is basically the exact opposite. Why doesn't, so if I pull outward on this pen, it doesn't go out. We would say tension, pulling inwards. But if I take the pen and do the opposite, I push inwards on the pen. Watch me real quick. I'm pushing in on the pen. Which way is the pen pushing my hands? out. Correct. So going back to my dumb picture, positive and negative, of course, are what we call, sorry, oops, nope, screwed that up, tension. But there's still negatives and negatives next to each other. What are those doing? Repelling. Those are called compression. If we zoom in crazy far on them. All right. Now, truth be told, on compression, we regularly don't use it because usually there are better options. But I do want you to understand what compression is. Next. Oh, if I haven't, I don't know which ones I fixed. Negative, negative on the first one. Negative, negative. Positive, negative. Negative, negative. Positive, negative. Negative, negative. I didn't mean to line them up like this. It just worked out. Springs. A spring is basically the exact same conversation as the last two. It's just that as I hold this spring here in front of you, it can be both, right? If I take the spring and I pull outwards, it's pulling in because of positive and negatives, just like tension. And if I take the spring and I push it inwards, it's pushing out exactly like compression. So why do we have a different one if it's basically the same thing as the last two? How do I know when to use spring versus tension or compression? It's really simple. Watch here and I'll show you, okay? If I take an object and I pull outwards or I push inwards and it does not appear to move, by the way, it actually does move, but it doesn't appear to move, we would call it tension or compression. If we have an object that then stretches noticeably, we would call it force spring. So things like a bouncy ball. Like if you hit a bouncy ball or just like a general ball, sorry, not that one. I don't want to drop that one right now. But like a basketball. When you press the basketball into the ground and it pushes noticeably, it compresses inwards. We would use force spring. Now, that's when you start to go, yeah, is spring the best name? Because you're not using springs at all. Later, we'll use another name for it. It works the exact same way, also known as force elastic. Okay, if you used force elastic instead, that would be completely fine. It's the same, 6 of one, half a dozen of the other. But again, spring is basically the same thing as tension and compression, same line of logic. It's just, does it stretch? Does it stretch or doesn't it? Finally, we don't always have a great option. What if we don't have a good option? Then we use what's known as random force. The example I gave you earlier with the marker being held in the air here is a great example. You go, okay, I'm trying to describe the forces on this pen. Spanauer is not a solid immovable object. So what should I use? Well, I know it's electrons on electrons, so what you do in that case is you use random. Now I have 1 and 2 here. These are placeholders, okay? 1 represents the object that's pushing, okay? The 2 represents what it is pushing on. So in this particular case, we would call this the push upward. If I used random, I would say the force of Spanauer, or let's not use Spanauer, too specific, okay? Force of hand on marker, something to that particular effect. Does that make sense? Technically, every force up here could actually be random force, but that gets very icky. Like, for example, gravity. I'm sorry, gravity's not up here. If I said the force of gravity on Spanauer, what I could say is the force of Earth on Spanauer, because those are the two objects in question. Or as the example that you see on here, what if a car is traveling down the road? Well, I don't have a great one for an engine, so I'm going to say the force of engine on car. We'll talk more about these in the next set of slides, though, so I'm going to move on. Okay. You'll notice, by the way, 5 and 6, I didn't talk about positive, negative, 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 because it kind of depends on the situation. Moving on. So let's give an example of random force here. So we have a situation.
No matter where you go in life, always keep an eye out for Johnny the Tackling Alzheimer's patient.
What's that supposed to mean?
Who am I?
Okay. So Johnny the Tackling Alzheimer's patient put a force definitely on the doctor going that particular way, but he's not force normal. It's definitely not force air friction or surface friction. It's probably not compression or tension or spring, so random becomes the best option. So what do? Well, you draw a picture and you draw something like force JD, and J stands for Johnny the Tackling Alzheimer's patient, and D stands for doctor. What's causing it and what it's on. Does that make sense? We'll practice with these a lot in the next coming couple days. All right, moving on. Okay, so if you heard the first two and you're like, holy crap, he's got 4, he's taken forever on the first 2. The next 2 go much, much quicker. We discussed the other day, there's a weird thing, there's a couple of weird things about the way the atom looks. Okay, one was that electrons are around the outside, and why is it not pulled inward? This can kind of be explained like planets, like we have a sun in the center of our solar system, and planets still go around it, they're not pulled in because they're going in a circle. But the other one was all the positives in the middle. Why is it weird that all the positives are in the middle?
Because they should.
And not just should, they do. They do repel each other. So what's weird is if they're repelling each other, how can they stay in the middle? Well, logically, we would go, this must mean there's some attraction holding them in. And they are held really darn close, which means that attraction better be super, super strong. And thus bringing us to the next fundamental force, strong force. We hit the nail on the head on this one. We didn't try to get creative. Strong force is the reason for the neutrons. A lot of times when you talk in chemistry or early sciences, they tell you that neutrons are there, but they don't spend any time being like, nobody ever asked the question, yeah, but like, why? Why are they there? They don't do anything with push or pull of negatives and positives. Why are they there? This is why. Neutrons and protons, so if you want to talk about that interaction like I was talking about before, neutrals and protons are what pull inward. And it is such a ridiculously strong force that, okay, if you move electrons on the outside of the atom, kind of move them around, shuffle them around, that's what we call chemical reactions. You use chemical reactions all the time. It's pretty much the primary focus of your chemistry and stoichiometry and all that type of thing. And when you talked about energy when you were in biology, you use chemical reaction right now. It's called cellular respiration. You break down C6H12O6 into 36 ATP and blah, 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 electron transport chain, yada, 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 muscles, active myosin. We don't have to get into that right now. If you came here in a car, you burn gasoline to make that car go. Okay, if you set anything on fire, you are changing it. You are moving every single one of those. The electrons are moving around. If you move something in the nucleus around, protons or neutrons, because of this strong force, it requires so much freaking energy. Do you know what the reaction is called when you move something in the nucleus? Yep, that's why it's called a nuclear reaction. Literally moving anything in the nucleus is a nuclear reaction. Big boom. That's how strong the strong force is. It is so strong that if you overcome it, big boom. Okay. The last one we'll cover just very, very quickly and say it's weak force that causes radiation. That's all I'm going to say. How many minutes talking about gravity, and yet we just knocked out weak force in like a half a second. Last 2 things to cover real quick is this. Out of the 4 of these, on our day-to-day lives, which ones do we regularly deal with? Gravity and? Pretty much. Yeah. Here's the nutshell, guys. If you fall down, it's gravity. If there's any other force on you, it's probably electromagnetism. These top 2 are the everyday forces. Why aren't we normally going to deal with the last 2? Because they take place in the nucleus and we don't really have to worry about them, because you don't usually see a lot of protons and neutrons moving around. You know how I know? There's not nuclear bombs going off in here all the time. Feels like that would be noticeable. Feels like we would go, yeah, okay, I'm not going to go to school today. How come? It's a crater in the ground. A nuclear bomb went off. So I'm just not going to go to the general space that used to be occupied by it. We're not going to call it school anymore. It's literally empty space. I mean, so. Now, let's talk about this. Let's rank them in terms of strength because this is important for later. If you had to guess, which one would you say is the strongest? Good call. Good call. Yep, if you want to rank them up here, first place goes to strong force. Absolutely. If you had to guess, which one's in second place? Electromagnetism. Nicely done. Electromagnetism is in second place. Now, which one would you think is in third? You'd like to think that, wouldn't you? Like, you'd like to think that we correctly named strongest strong and the weakest weak, but you would be incorrect. The second weakest is the weak force. And the weakest force that we know of is gravity, which is why you need so much crazy amount of mass in order to pull off any sort of significant impact. So yes, definitely have this in your notes. First, second, third, fourth. All right, key points that we discussed real quickly, launching through them. Force of gravity is the exact same thing as weight, but what am I going to say? What am I going to say?
Mass not the same thing.
Weight is not mass. Mass is not weight. All right, your weight depends on two masses, and I don't like it's not up here. I'm going to add this later. And a distance. And a distance. Electromagnetism that we regularly deal with is just tiny positives and negatives. Like if Keyser is up here and I'm annoyed at him because of an email he wrote and I give him a shove, okay, that's electrons in my hands and electrons on him, okay? If he gets annoyed because of how often I bring him up and he slaps me across the face, hypothetically, he didn't actually do it because we are recording right now. All right, and I feel a mark on my skin, it's probably because the positive in his skin held on to the negatives of my face and pulled a little bit, which broke down some of my skin, and of course my skin is now red because of the blood that's coming to there trying to heal it. It's not an important thing. That's more of an anatomy conversation. And finally, common forces that we regularly deal with are really just electromagnetic. You don't have to write any of these, by the way. They're just already in the notes. And you should know when to use all of these particular forces, which we are going to talk about a lot more in the next notes. How do I use them and when? So if you're sitting there like, I don't know how to use those forces. The thing I do want to point out here is, I've said this before, but watch this. That one is force of gravity. All of the rest of them are what? Electromagnetism. Correct. And you will notice there's no strong or weak up here because we don't deal with it on a macro scale. And that is the second part of fundamental